Thanks for the introduction. Um, Back, quit. Okay. And we still work? Yes, you're right. Okay. All right. Hi everyone. I'm very happy to be here. I thought it was my second time, but actually maybe it's my third time. So I don't remember the first time. So it's a good sign. Uh, and I want to talk about quantum error correction in with superconducting qubits. I initially prepared for 2 hours, but then Rafael told me 2 days ago there is 3 hours lecture. So please ask many questions, otherwise I don't have enough material to cover. And I want to talk about error correction in general and about superconducting qubits and tell you the basics, but also I want to cover some work that we've been doing at Amazon Web Services in the Center for Quantum Computing on bosonic quantum error correction, which I'll explain what it is, and I'll also tell in a little bit more detail some of the recent experiments I'll be doing and our plans for the future. All right. So again, please ask questions along the way. So let me start, and just to motivate, right? Maybe this, we all know this, but I think it's always good to understand why we are all here, right? Talking about quantum computing, and to start talking about quantum computing, I think it's very interesting to first look at classical computing, right, and how it has evolved in really an amazing way in the past, like 70 years or so, right? So we have seen this scaling in the number of transistors that we have in a chip, or in the number of compute power of a chip, exponential scaling, where we double the number of transistors that we have on a chip basically every 2 years, and this has been the case for the past 50 years at least, right? So in the early 70s, we start having computers that could do some interesting stuff, but they had, right, like maybe a few thousand transistors, maybe a little bit more. And now in the GPU, we have 100 billion transistors, right, in a single GPU. And that's just an amazing amount of compute, right, that we have. And that's great, but still, right, if you look at some problems, even this amazing amount of compute that we have today is not enough for solving them, right? So this is a plot that many people use, and I like to use it as well, which is the use of the supercomputer of the Department of Energy of the US, of the Department of Energy of the US, and I think it would be typical distribution for other supercomputers as well. And what you can see here is a breakout of which fraction of the time of the supercomputer was used for many different areas that people care about. So like environmental science is the number one, fine. But then look at all the next ones, right? Like chemistry, material science, fusion energy, nuclear energy, high energy physics. This is all about simulating complex quantum systems, right? So what we find from this is that there is this kind of intrinsic hardness of simulating quantum systems, and a lot of our most powerful computers today are used to solve this problem, right? To simulate these complex quantum systems. And of course, these are all important areas, right? Like material science, chemistry, right? For the development of new technology and of society. So then, okay. And why that's the case, right? So there's a lot we can talk about this. But on a very high level, in the worst case, the cost of simulating quantum systems grows exponentially with the number of particles, right? So if you want to simulate 50 quantum spins, spin half system, this takes like 10 to the 50 memory. If you want to go to like 100, right, particles, this is like 10 to the 30. So there's this exponential growth. Of course, there's many methods that we can use to do it approximately. There's many clever ideas we can use, but this worst case appears to be like this exponential cost of simulating quantum systems, right? And that's, of course, a big challenge to simulate these quantum systems. But maybe we can also, right, see in the opposite direction, and maybe that's an opportunity for us, right, to just have better computing. And the first to mention this idea, this is not confidential. I don't know why we have this, but I wish this was Amazon confidential, this insight, but no, I don't wish. That won't be good for all of us. So Richard Feynman, right, in 81, he had a very influential lecture on computation in physics, right? And he has this quote, which I think you all heard, but let me say it again. He said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy," right? So So that's the seminal idea of a quantum computer, right? So let's just use quantum systems to build a new type of computer, and at least for simulating quantum mechanics, it ought to be a very good computer, right? That was his insight. And what we learned in the past like 40 years since these insights, that there is like a main claim of quantum computing, which we are all trying to validate in a sense, which is that quantum circuits, right, which is a way to make quantum computing concrete as a computational model, can solve some problems, not all, but some problems with exponentially fewer gates than classical circuits, right? So that's like a remarkable fact, right, of nature, and really quantum computing is the only model of computation, right, that we think we can realize in nature that gives this exponential difference, right, to classical computing. So like it's a refutation of like this strong Church-Turing hypothesis, right? So that's very interesting scientifically. Maybe it's interesting technologically as well, right? If like these problems, if there's some problems, right? If it turns out these problems they are actually relevant for society. And there's two main questions here, right? So what are these some problems, right? Which class of problems we have this? We don't know. We know some examples, but we don't really know. Are they really useful? And second, is this really a model of computation that we can realize in nature, right? And that's the second question is the one I want to address here. But first, just mention some of these problems, right? So going back to Feynman, right? So there is, of course, simulating physics and chemistry. For example, one example is like simulate molecules. It could be simulate some many-body model, like the Fermi-Haber model as well, and so on. And then if you look at the quantum algorithms for doing that, we need from 100 of qubits upwards, and we need from 100 million gates upwards, right? So not too many qubits, but a large number of gates, right? If you look at like cryptography, right, which is the most famous example that Peter Shor showed in '94 that you could break RSA, which is the most commonly crypto system that we have today. You could do that with like thousands of qubits. It keeps changing, but like a few thousand, but you need like 10 billion gates. You need more gates. The material science, right, similar, right? Again, I think here is you can think about like simulating Fermi-Haber model or simulating some batteries, something like this. Again, not too many qubits but millions of gates. And then there's like all these more speculative applications, which could be more widely applicable, right? But that we don't really know if there is a speed up or not. And maybe there is a speed up, but it's a smaller speed up, it's not exponential. And then you have to be careful, like in stuff like scheduling, resource allocation. Sometimes people explore even AI, although it's very speculative. And again, like not too many qubits, but a lot of gates, right? So that's kind of the point here. So to get to some potentially interesting applications, we won't need too many qubits, but we need a lot of gates. There's a question. That's the reason why I put it. Yeah, it's just that. Yeah, right. So you want to get a square root. You have a square root speed up, and you want to solve some combinatorial optimization, right, with 100 variables, and then you need a lot of time steps, right? So yeah, thanks. Good point. All right. So just a little bit more detail, right? So this, like we want to run these circuits, right? Like prime factorization is some kind of like a phase estimation for this model exponentiation. We want to do quantum chemistry, which is a similar circuit like with phase estimation. And then people can come up with these tables, right? We did some review paper that we had at Amazon, where, for example, here you look at some different molecules, like there's like Femoco molecule, or some molecule associated to some enzyme for drug development, or some molecules associated to battery development, and so on. And then you see like the number of logical qubits, right? Which is this range that I mentioned from 1,000, sometimes it can be more, right? But then if you look at the number of gates, and this we count in terms of Toffoli and T gates, there are other gates as well, but considering those, you see these very, very high numbers, right? Like, billions of gates. And great, so, billions of classical gates is no problem, right? So again, a single GPU makes like a billion gates, actually many, hundreds of billions of gates per second, right? But transistors have no errors, right? So transistor, like really the error rate of transistor is like 10 to the 19, something like this, right? 10 to the minus 19. So we don't even, we don't care about it at all. But if you want to run these applications, we would need, maybe the gates can have a little bit of error, but the errors will have to be like 10 to minus 10 level, right? And that's kind of a challenge, right? Because if you look at where are the error rates in the experiments that we are building today and we have built in the past 20 years, there's quite a big gap, right? So like it's been improving, so that's a good thing, right? So like 15 years ago, like we had like 10% error rate for a 2-qubit gates, right? In many experimental platforms. 5 years ago, it started getting better. It was like 1%. Today, it's like getting better again in many different settings. We are approaching like 10 to minus 3 error rates, 0.1%. So that's all great, right? But if you look at the target that I mentioned, right? So we want to have 1 error every trillion gates, right? So it's a huge gap here, right? And if you just think about this incremental progression of just making the experiment better in the lab, first, we never know if we can really reach this level, right? Like, can we build a quantum transistor? That's like a very big open question that most people are skeptical, right? You can just build a single qubits in the lab and gates which are precise to this very, very high level. And second, even if you just extrapolate the trend, it's like 50 years out until we're here, right? And we don't want to wait 50 years. So, that's kind of the second question that I mentioned. That's the key challenge of quantum computing. How we reduce error rate like 9 orders of magnitude, right? That we want to reduce to run the applications. So that's kind of, that's should scare everyone, right? But that's the challenge that we have to address, right, in the field. And I hope to convince you that is possible, right? And that we might be doing that like the next 10 years instead of the next 50 years. Any questions? All right. So how people are trying, right, to build a quantum computer and address this challenge and eventually run some interesting applications. There is many different platforms that are being used, and I want to mention them just to, that you are aware, right, of the main ways, and then I will focus on one particular one, the superconducting qubits that I mentioned. But here is like pictures of, these are like a superconducting qubits, right? There should be the names here, then put. So this one is like using quantum dots, like spin qubits. This one is with ion or photonics, right? Linear photonics. This one is neutral atoms, and this one is ions. Let me check if that's right. Yeah, so I got it right. And then they change, of course, right? How you build the qubits. They also change how you control the qubits, right? And then there's many characteristics that we care about, which is like how scalable they are, how fast are the gates, how fast is readout. They also change. So there's a lot of diversity here. And basically everyone is picking up bets, right? And just seeing which of these bets is going to work out in the future, which is the right thing to do, right? Because really, even though I'm working with superconducting qubits and I'm of course excited about this, no one knows, right, which one of these is going to be the one that we actually build a quantum computer. No one knows if actually we'll be able to build with any of those, right? Maybe they all fail and something else will emerge. But anyway, so there's 3 things that I want to mention here. One is like how you do the classical control, how you control the qubits. One is how you do the manufacturing, and one what is the scale that we have today of this. And the next slide I'll tell you more stuff. So for superconducting qubits, the class control is done with kind of microwave electronics, right? So you just send microwave signals inside a fridge and that attach to the qubits and send the microwave control there. The manufacturing, that's a nice thing about it, which is using this, not entirely, but like using microfab to do it, right? So you can say that it's using the same methods that are being used to build, the computers from today, which is a great thing because, like this industry, right, this Moore law, right, it's this amazing exponential growth, and that only happened because the most sophisticated industry ever built was built to do that, right, which is the micro fabrication industry, right? Now, it's not entirely true because we need new fab processes in all of those, free that use microfabrication. So it's not that we can just go to TSMC or to Intel and say, oh, just fab the quantum chip. It requires some modifications. We make it challenging. But it's nice that we have this backbone, right, to eventually be able to scale to millions of qubits, billions of qubits, and so on. And the scale that we have today, like I'll mention some experiments, but like performing well enough is like hundreds. People are trying to push to 1,000 these days. Then for spin qubits, again, is electronic control, is microfab again, which is nice. they haven't been able to scale so much, but it's like, orders for like 10. Error rates are also high. I'll show you that. Then optical, again, you can do like silicon photonics. So microfab, again, you can do it, which is interesting. But it's very hard even to get 1 qubit, right? Because, just photons don't like to interact. You have to create some huge delay lines. It's a pretty daunting task, but people are also trying to do it. And then for the atomic approaches, so first, these like neutral atoms, like Rydberg atoms, if you have heard, is developing very fast these days. It's very promising, I think. And the classical control is optical, right? So the qubit is like storing the electronic state of the atom to hyperfine states, for example, for 0 and 1, and the Rydberg highly excited state just for making the gates. These are all optical transitions. Manufacturing, really, you have to be like atom by atom assembly, right? Or ion by ion in the ion trap case. So, this is a less developed way of scaling to millions, billions of qubits, right? So, which I think it's a disadvantage here longer term. But they do have an advantage of scale happening right now. So they are able to, have like 300 atoms already kind of applying gates and so on. And they have very clear path for like 10,000 atoms, which I think you'll see in the next few years, experiments with 10,000 atoms doing gates and doing error correction, which would be exciting. And ions, very similar, optical transition, ion assembly in this case. They have like 100 ions right now and very interesting experiments. But I think the scaling will be more challenging than for these neutral atoms, in my opinion. Although, of course, people also have ideas how to do it. So how are the other things then that matter for scaling, right, and for running applications work in these cases? So here I list again these 5 platforms, which I think are the main ones being developed, right? So if your favorite one is not here, I'm sorry. So you can please tell me and I'll edit. But these are the ones that people are mostly doing. So and what are things that you care about? Of course, you care about to scale, right? And I'll tell you why you have to scale. And the reason to scale is to solve this key challenge, right, of reducing the error rate, which, spoiler, but I think you already heard in the other lecture, right, is using error correction for that. So scaling is very important. But also, because again, right, you have to apply so many gates, the time that it takes to apply gates, right, with error correction will matter as well, right? Because otherwise the computer is just too slow. And even though you have this exponential speed up, if it takes like many years to factor a number, that's not good, right? So you have to care about the time of all these operations as well. So here is very biased, right? So because it's my opinion, but I want to give your opinion. You can have different opinion, that's fine, and we can debate. But I look at gate error rates, right? So how easy it is to get low gate error rates, right? We want that as low as possible. And I'll also think about gate time, how fast the gate can be implemented. Also, because we're going to do, spoiler in error correction, the readout time is very important. So I also look at readout time. Scalability, how easy it will be to scale, so the scales that we need to get a useful computer, which is like hundreds of thousands or maybe millions of qubits. And some examples of who is working on this, right? So for superconducting qubits, which we'll be focusing from this slide on. So gate error rates, it's kind of low given the state of the art. The gate time is fast, that's very good. Readout time also is fast. Scalability, I think, is kind of medium. Again, it's nice to have this microfabrication, but there are many challenges, and I'll tell you what they are. And Google is doing that, IBM, and we are also doing it among many other people. Then silicon spin, the gate error rate is still substantially higher than for other platforms, than definitely superconducting qubits and definitely atoms, which are very good gate error rates. It can be fast as well, the gates, though. Readout time is a little bit slower. So this is like microsecond, right? So giving you a scale. Gate error rate is like 10 to minus 3. Gate time is like, it varies a lot, but it's like from 25 nanoseconds to 100 nanoseconds. Readout time is like 1 microsecond, maybe several hundred nanoseconds. Here, gates, it's hard to get like less than a 1%, right? Gate error rates, so it's still kind of high. Gate time is similar, like tens of nanoseconds. Readout time, I think, is like 10 microseconds. Scalability, I think, it's kind of hard because on one hand it's very good because they are very, very small, the spin qubits, and they can operate at higher temperature than superconducting qubits. But because they are so small, it's very hard to control them, right? To put the wiring to control them. So it's a little bit harder than superconducting qubits, in my opinion. Intel is doing it, and other companies. Then photonics, gate error rates actually can be even higher than the other ones. Can be, like a nanosecond or a couple of nanoseconds. sorry, no, gate error rate, we don't even know. They don't have 1 qubit. It's kind of hard to get 1 qubit working. Gate time can be very, very fast. Readout time is fast as well. It's like, again, I think microseconds. Scalability, in my opinion, is hard, but like if you talk to PsiQuantum and Xanadu, they'll say, no, we have a plan, we'll get there. So, okay. So atoms and ions, they are progressing very nice, in my opinion. Gate error rates is a little bit higher than superconducting qubits, but I think they have a clear path for like 10 to the minus 3. So that'll be nice to see in the next few years. What they really pay, I think, is gate time. Gate time can be made fast enough, I think, but readout time, well, actually no, gate time, because they move atoms or ions around to really get this good scalability, and moving is slow. Moving is like tens of microseconds, right? So instead of like tens of nanoseconds, you get tens of microseconds. So there's like a factor of 1,000 here, which I think will be an issue long term. Readout is also slow. It's like a millisecond. Maybe can be made faster. Scalability, very good in the short term. I think to 10,000 to 20,000 qubits, they have a much better path than anyone else. To go to 1 million qubits, then I don't know, because you might need a microfab, right? So there's different challenges. And many experimental teams are doing this at Harvard, at Caltech, and there's companies as well like QEra, Inflection, and so on. Trap ions gates are very, very good, especially like two ions, you can get the record, right, gate error rates, less than 10 to minus 3. Quantinum also has very good, like 90-something qubit system, right, with all 10 to minus 3 error rates, so it's great. Again, as slow as ions, as atoms, so kind of slow, I think, for long term. I think they all know that they have to find ways to speed up the gates, and without which, I think that, there might be ways. Scalability, I think, is harder than atoms, in my opinion. And there's IonQ, but Quantinuum, I think, is ahead. They're doing very nice experiments. So this is kind of the landscape, right? And again, this is very subjective. It's just my personal opinion. Yes. Everyone can parallelize gates, right? So it's not, I'm not taking that into account, but the application, for example, when you factor, you already take into account that you parallelize many, right? Everything. Even for error correction, you have to parallelize the gates, right? So, yeah. Any other question? Oh, right. Good point. Yeah. That's a very good point, and it goes to this, which I will mention just in passing, but let me already mention now, which is if you can do long range gates, right? Gates among every pairs of qubits, this opens up the the space of quantum codes you can have, and nowadays we are finding better and better codes called like quantum LDPC codes, which allows for much better overhead, which is the ratio of like physical to logical qubits. And neutral atoms and ions, they can move the atoms and the ions around, so they can do these long-range gates, which is the reason why the gate time is kind of slower, right? So it hasn't been done yet. Well, actually, it's not being done. Actually, there was a paper yesterday from Continu, very interesting, where they might actually be able to pack a lot of logical qubits into this kind of 10,000 or whatever physical qubits they will get, right? So that's very exciting. IBM is trying to do the same for superconducting qubits, but it's way harder. And yeah, I don't think there is ideas for silicon and for photonic. You can also do it a little bit. Yeah, no, right. I think you care to, and I don't think we have figured out all the ways the long range helps the logical error at the logical level. But there's a paper. Yeah. Yeah, that's right. That's right. I think the first one seems very, very. I mean, it seems more valuable than the second one for what we know now. But even in the second one, there's some examples where it helps. So one particular example is Daniel Litsinski had a paper called like active volume, which is just a way to compile quantum circuits, and he shows that if you have just kind of you have n logical qubits and you have some kind of log n long range connections between them, then you can speed up a lot factoring, for example. They have better algorithms. So that's right. So exactly. Yeah. So this which is similar in classical computing as well, right? They play all these kind of games. So I'm sure the same will be played in quantum if you have this. All right. Yes. I'm considering optical, and it's true. Both the gate time, like is low. Maybe if you compare, like here can be like tens of nanoseconds, right? I think that's I haven't seen like ion traps getting close to that, but they're getting low, right? So I think gates. Well, okay, it depends. So if you just count the gates, like doing the optical right interaction when they are close by, this can be made faster, right? But if you count about the time to move them around, which I think you should count if you want to think about the architecture, then this is where you get this like tens of microseconds, right? Yeah, right. That's right. But of course, you can think about an ion or atom architecture, which is just stays local, right? But then you lose a lot of this scalability advantage that you're getting from moving, right? So. Majorana. I mean, I'm not an expert first, but it has shown to be extremely challenging, right? So we don't have right. So the idea of Majorana is that it's the idea of this topological quantum computing, right? Which is an idea, very elegant idea, where if maybe you can just engineer material. It's almost like, let's try to find the quantum transistor, and there is a phase of matter that maybe gives this quantum transistor, which is topologically protected systems, right? These topologically protected systems, they exist, for example, in 2 dimensions or higher dimensions, and then you can have ground states, which are which form a naturally error correcting code, right? And some of them maybe in 3 dimensions or more. Actually, we only know in 4 dimensions or more. They can have even be self-correcting. So in that case, really almost you do get a quantum transistor, but you just need a high number of dimensions. In Microsoft, for example, and a few other places, they've been trying to do a version of this, but like there's like a Majorana chain, and in the end of this chain, there is like a protected qubit. And the goal won't be like this kind of transistor, but the goal is that it will be a qubit with a much better error rate than you can get in the other platforms, right? So sometimes they say, okay, the best we can do here today is like 10 to minus 3, right? Error rates. They say, maybe if you do this in the right way, with the right disorder, this gets like 10 to minus 5, or it will be something like substantially better. The issue is that they haven't been able to do that yet. They haven't even been able to confirm that they have a qubit right in the end of this chain, that the experts say, okay, you have a qubit. Just a very messy system. There's a lot of disorder, right? There's a lot of like complicated interactions, and the signatures of these qubits, gets mixed with other things they have in the system. So even like just let alone having a good qubit, just saying that you have a qubit that is still kind of open and debate. There's a lot of debate around this. So I don't think it's in my opinion, I wouldn't open a startup doing Majorana qubits right now, but yes. Right. That's a good point. You mean Xanadu, right? Xanadu did that? Yeah. And I'm not aware of the details of that paper, so it's possible that they do have a qubit, right? So sometimes they do GKP, but it's a slightly different setting where, and I will talk about it, right? It's like more bosonic error correction, right? So you have like a resonator, you have, for example, light in this resonator, and then you can create some, encoded protected qubits there. I was thinking more about just this silicon photonics, right? With just like dual ray of photons, right, propagating there. But maybe Xanadu has a different architecture now. They might have. I'm not just not aware. Or maybe just, we have to update this. Is a good call out. Thanks. Okay. All right. So, okay. So, I missed this slide, but now I will be talking about superconducting qubits, right? Which is what we're doing at Amazon. And again, why? Well, because we think it's promising, but not saying that the other ones are not promising, because we're just too early to know, I think, who will win this. But how then, this works, right, for superconducting qubits, but also for the other ones. So in the end, the quantum, right, we always interface with a classical computer. We always program the quantum computer using a classical computer. So there's like you want to send a quantum circuit, right? So there's a compiler that just maybe maps some higher level abstraction to the quantum circuit you want to send. We actually don't send instructions in terms of apply a C0 gate, apply a X gate. We have to send like pulses, right? In the case of superconducting qubits, as I mentioned, is like some microwave pulses, either some flux pulse or maybe some actual microwave pulse, XY line. So there is like a compiler, right? The map to control pulse layer. There might be some error correction that we're going to talk about. So there is some error decoding layer, for example, for the error correction. And this is done talking a classical computing, talking to a system that converts digital signals, right, coming from the decoding layer and from the quantum compiler layer into analog, right, signals, the control pulse layer that is sent inside first some environmental shields. We want to, for example, just protect the qubits from the magnetic field of Earth, right, and other things. Then there's all this wiring has to come down. So to a package shield, similar to we do classically, we need like a package to protect again from electromagnetic radiation outside. And then there's all these wires coming in, and there will be the quantum chip here, right? And this is all inside the refrigerator just to keep things very, very cold. That we don't have to care about thermal excitations. So this is, our lab there at Amazon. So you have seen this for sure, right? There's all these refrigerators that many companies use, these cryogenic refrigerators for cooling the system. So this is a picture of the refrigerator. This is all this control wiring that we need, right, to control the qubits. At least one. Okay, right now is like a couple wires per qubit, right? So I think we have to develop multiplexing solution in the future, but that's how we do right now. Then there's this magnetic shields, right, that we have. It's just like this tube here. Here's another picture of it. And then at the bottom of the chip, where the temperature gets lower in stages in this cryogenic refrigerator. At the top of the fridge is like roughly 20 millikelvin, so very, very cold. You have the package, which is this gold stuff, and inside the package you put the quantum chip, and then the package allows you to just put all the wiring in, and then you kind of wire bond to the chip, right, to send the signals in, these microwave signals in. So that's how it looks like, right, the system. And then we need people think about the cryogenics. We need people think about the wiring, right? And of course, most of the work is people thinking about how to build this chip, right? Okay, so what is the main physical process that we use in superconducting qubits, and why it's called superconducting qubits? So the idea is that we, again, similar to how we think about in classical computing, we look at electrical circuits, right? So here, for example, is a LC circuit. But suppose you build a LC circuit, and suppose you just cool it down to very, very low temperatures, right? So at very, very low temperatures, things get quantized, right? So there'll be the Landau levels here. And so, for example, if you look at the current, right, the current will only have pre-specified levels, right? So discrete levels will be just like a quantum harmonic oscillator, right? So that's fine. So then you can say, oh, okay, so maybe let's use the levels of this quantum harmonic oscillator for the qubits. But that's not great because they are equally spaced, right? It's a quantum harmonic oscillator. So if you send a signal and you excite ground to first excited state, you also excite first to second excited state and so on. It's just a mess, right? So to get a qubit, you wanted 2 energy levels, which are, for which the gap is distant to all others, right? Then you can address the qubit. That's how, that's why atoms are nice. And so we need a nonlinear process here, right? And the way to do this nonlinear process is an idea by Josephson, and he got a Nobel Prize for this many years ago, which is this gadget called Josephson junction. So first, we don't want dissipation, right? Dissipation leads to loss in the qubit, to errors. So we make things as without dissipation as possible. There's good ways to do that, right? It's just using superconducting materials, right? So we look at an electrical oscillator, so a LC circuit, but a superconducting LC circuit. So we just use a superconducting material. So we use aluminum, for example, is one popular choice. We can also use tantalum, is actually a better choice these days. And this is a superconductor. But now we want to make, the capacitor, we just build a capacitor, like how you think about it. But the inductor, we don't want to do a linear inductor. We want to build a non-linear inductor. And for that, we use this Josephson junction. So this is just two aluminum islands. But then you put a thin barrier, like, this is like a few dozen nanometers, for example. It's very, very, very thin, of oxide, so aluminum oxide in the middle. And then this is an insulator, right? But because it's not a very thick barrier, there can be tunneling here. So the aluminum is a superconductor, so there's like Cooper pairs, right? The electrons, they pair, they bond, and that's why there's no dissipation. And then you can tunnel, Cooper pairs can tunnel from here to the two islands. So there is a current, right, going through because of tunneling. But now this current will be, like the inductance of the current of this inductor is nonlinear. Okay, so it really depends on the number of Cooper pairs there. So then is a nonlinear harmonic oscillator what you get in the end. So this is the symbol for the Josephson junction. It's just like a box with a square. And this you get like a nonlinear harmonic oscillator, where the two lowest energy states is where you encode your qubits. Okay, so that's why we have to build in the lab. We have to build this kind of electric circuits using microfabrication techniques. I'll show you a picture. But there is two differences from the way we do these days, right? So the first, three main differences actually. So the first is that we need superconducting materials. So a lot of the fab processes are not for really aluminum. We have to develop processes that work for superconducting materials. That's one challenge. The most challenging part of this is building the Josephson junction, right? You have to build this well, like as precision as possible, right? So if you see, there might be like defects in the junction that creates decoherence for the qubits. We have to avoid this. And the second is that in the electric circuits that we operate, is like the volt scale, right? Is the scale of like an AA battery, right? That's what you should think about. Whereas the scale here that we operate is microvolts, so it's like 1 million less, right? Like electrons here. So then you have to be careful about this, right? It's just microvolt levels. So this is like how we do the chips, and this is how again, this is like you start with a wafer, a silicon wafer, exactly how you do classically, right? Then you go to a fab. There's many fab processes, right? Basically, you do like some deposition of some layers, you do some lithography, do some etching, right? And then you like start sculpting, right, the circuit that you want there. So this is like, for example, a 4 inches silicon wafer, which is like a 10 centimeter wafer. And then our quantum chip in this case is 1 centimeter by 1 centimeter. So you have like 100 copies of it here, right? And then if you zoom out, you see like many things, which is like to send the signals in, but the qubits in this case will be here at the crosses. And this is how you do it, right? So you just basically manufacture the qubits doing fab processes, which is nice because it gives you flexibility about many things, but it's not so great because, atoms, nature gives it to you, right? They have very specified properties, very specific, right? That they're set in stone. Whereas here, there's all kinds of problems, right? There's like, two-level systems defects, right? There is imperfection in the Josephson junction size, which leads to imperfection in frequency and so on. So there's a lot of fab challenges that one has to address. But that's kind of the game we're playing, right? So just trying to make fab reliable enough that we can build good enough circuits. And then maybe if we can do it, we can scale more easily. Because, right, of course, there's a whole industry that's just about scaling this kind of, right, microchips. All right. So now let's get then to the main question, right, that I asked, this key challenge, which is how we are going to reduce the error rates by like 10 orders of magnitude, right, 9 orders of magnitude. And the reason why, many of us believe, right, that we can do it is because there's this idea of error correction, right? Or in this case, quantum error correction. But of course, this idea that we got inspired by what we can do classically, where error correction is also an important idea there. So let me talk about this now. Any question before I move on? Okay. So let's start talking about errors, right? So we have a bit, classical bit errors, right? That's all. That's the type. The only type of error you have for a bit. A 0 can become a 1. A 1 can become a 0, right? This we call a bit flip error with probability px. So how So again, when we do computation in the classical computer, we use transistors. These transistors could have an error rate, but this error rate is so small, like 10 to minus 19, if I remember correctly, that you don't care about it, right? But when you, for example, send communication through an optical fiber, or when you store some information in a magnetic memory, there is an error rate there. The error rate can be actually pretty high, can be like percent level for magnetic memory. And then you have to find a way to handle errors. And the way to handle errors is to use, to store or to compute using redundancy in your information, right, in your bits. And that's what error correction is about. So there is very simple error correcting code classically. It's called repetition codes. What you do is, if you want to store a 0 in a magnetic memory, you store a bunch of zeros, right? In this case, like 7 zeros. And if you want to encode a 1 in the memory, you store a bunch of 1s. In this case, again, like 7 1s. And then the idea, suppose the error channel is not too bad. It's just like some stochastic error channel where you just, for each qubit, independently of the others, has a probability p of flipping. Then like if at most 3 of them flips, the majority of the bits are still in the right state, right? So if 3 of them here flips to 1, 4 of them are still 0. So you just read out all of them, do majority voting, and then you can decode, and you are successful, right? And the same thing here for 1s. If at most 3 of them become 0, you can still correct the information. So by using more bits, right, to store 1 logical bit, in this case, we can reduce the error rates. And the error rates, if the errors are roughly independent one from the other, the error rate decreases exponentially with the size of your encoding block. Okay, and that's the code. So this is our building, right? This AWS Center for Quantum Computing is on Caltech, and one of the things, our main thing that we're trying to do there is to kind of use this idea of error correction in the quantum case, which everyone is doing these days. But as I'll tell you, there can be an overhead, right? Which is exactly what is the overhead? In this case, was 7, right? You go from 1 bit to 7. In the quantum case, can be even much higher, and this becomes a challenge. So our main goal there is to research ways to implement quantum error correction, but as efficiently as we can do. And I'll be telling you one approach that we've been working on. And this approach will be like using quantum error correction, but this bosonic variant. So now I want to tell you what is this about. But let me start with just talking about error correction in general, right? And of course about the qubits. So we all have seen the qubit, right? So we can put it in the Bloch sphere. It's just a superposition of ket 0, ket 1. I told you about one way to form the qubit, which was this transmon, right? So we have this harmonic oscillator. But now, because of the Josephson junction is not a harmonic, right? It's anharmonic oscillator. So there is the gap between 0 and 1. It's larger than the gap between 1 and 2, which is larger than the gap between 2 and 3. How different the gaps are is like 200 megahertz. So this gives the scale of how fast you can do the operations. So that's one example. That's is the main qubit for superconducting qubits. There is other qubits as well you can build, but this is one of them. And of course, this is another example. These neutral atoms, right? Just what is the qubit there? It's these hyperfine qubits, right? These hyperfine levels. They form 0 and 1. They are very long-lived. That's great, but they're not good for gates. So then you also use the auxiliary level, the Rydberg level, to make the gates. And again, right, you could talk about ions as well and so on. So this is the qubit. But now the qubit is richer, which is great because this maybe leads to these exponential speedups that I mentioned. But because it's richer, there is also more types of noise, right? But early days, the skepticals of quantum computing, they will say, no, this is analog computing, which we know can solve even NP-hard problems, but it's not practical because just errors destroy it, right? And they'll say, well, there is infinitely types of errors in quantum mechanics, right? Because the qubit is a continuous object, so the errors are also continuous. You can have a very small rotation, right, about any direction you want, and therefore error correction will never work. What's remarkable about quantum mechanics is that actually there is more types of errors, but it's just like one extra type of error, right, instead of infinitely many. So we do have the bit flip errors. They just cause in the kind of a error where a 0 becomes a 1 becomes a 0, exactly like classically. But now we also have what we call a phase flip error, which is just a bit flip error in the rotator base, in the Hadamard basis, right? So a plus, which is 0 plus 1, can go to a minus, which is 0 minus 1, and vice versa. And this we call a phase flip error. And the claim is that kind of, every error model that we can experience in nature, you can think of a combination of bit flip and phase flip errors, right? So that's one important claim of quantum error correction. And why that's the case, who knows? Sorry? Yeah, the question is, there's all types of errors that could happen in a quantum system, right? So for example, you can have a small misrotation around the x direction, right? But I claim that if you are correcting for bit flip errors and phase flip errors, you should be able to correct for any type of error. Exactly. Yeah, that's the answer, right? So this small rotation you can always always write as a linear combination of the three Pauli matrices, right, and identity. And the Y Pauli matrix is a product of these two, right? So any process you can think of as maybe it's happening in superposition, but as an error of a bit flip, phase flip, and product of them happening, right? So it's very interesting because of this Pauli, right? Because of the Pauli basis of operators, we have a discretization of error in quantum, and therefore we have a hope of using error correction instead of these infinitely many errors that we could think. Yes. Yeah, then crosstalk you'll be a correlated error, but there'll be a XX, for example, or YY, right? Or yeah. Yeah, because a multi-qubit operator can also be written in a Pauli basis, right? But with XY products of Pauli matrices, right? Yes. Sorry, say again? Yeah. Oh, you won't see. Yeah, leakage you have to introduce. Yeah, that's right. So this is a great point, which actually is very important for superconducting qubits. This is assuming that your qubit is really a two-level system, right? But I just show you there is never a two-level system, right? So in the Transmon case, there is all these higher energy states. In the atomic case as well, right? So sometimes the qubit just is not a qubit anymore, right? It goes to a higher excited state, right? And you have to handle that. And of course, that's not mapped here, right? But then this leakage error, we have to address them as well, and we do, right? You could also write a basis, right? You could also think about like a higher dimensional versions of this, right? But usually just think about this for the qubit, and leakage we treat separately, right? It's an easier way to model things. It's a good comment. Thank you. Any question? Okay. All right. And of course, repetition code or a classical code is no longer sufficient for quantum error correction, right? So now we have to develop new codes, and these codes, they have to correct bit flip errors, and they have to correct phase flip errors as well, right? All right. So I'm going to tell you how to do the quantum code, but let me mention actually just more about the repetition code, because I want to use similar kind of notation here. So the repetition code that I show you, right? So you just 1 0 becomes many zeros, 1 1 become many ones. And now, as I mentioned, right, one logical bit constructed from 5 physical bits, it can correct up to 2 bit flips, right? If just 2 flip here, then the majority is still the right one, so you can correct. And if you just imagine that there is a probability of physical error rate P independent in each one of them, the logical bit flip error rate, right? So how your logical information is being corrupted now goes as the physical error rate to the power of 3, right? Because only 3 errors lead to error. So you have this kind of nice exponential suppression with the size of the codes. So that's what I told you. But now let me complicate things here, because then the quantum becomes easier. So the data qubits, I will introduce like the data qubits, which is this what I drew here before. There's 5 of them, right? So D1, D2, D3, D4, D5. But now I told you, do majority vote to the codes. Now let me do something else, right? Let me introduce some extra bits. This is called like ancilla bits. It'll be like A12, A23, A34, A45. And I will do a very simple local computation on these ancilla bits, where I just look at the parity, right, of the 2 nearby data bits. And I'll suppose, that this data bit was corrupted, right? A 0 becomes a 1. Then here, right, okay, and at the boundary, okay, so then for this ancilla, you'll be like a 0 and a 1. So this becomes a 1, right? This ancilla, the next one, is also like a 1 and a 0. This becomes a 1 as well. This one is 2 zeros, this is a 0, this is 2 zeros, this is a 0. So then because these two flag, right, these two ancilla bits are 1, we know that the error happened here, right? If the error happened here, again, these two neighboring ones will flag and so on, right? So this is a way where, we do the decoding locally just by looking at this kind of, ancilla qubits, and if they flag two neighboring ones, you know that the data in the middle of them is the one which was corrupted, right? Great. So with that, how we do in the quantum case, right? So there is many codes, and I think Josias maybe already covered this, but let me cover again. The most popular way of thinking about error correction, for a long time, people really thought this was the best way of doing it. But now I think there's many different ideas, and I if I have to guess, I think when the quantum computer will be built, it won't be using surface code, but maybe some variants. The idea is to try to do something similar to what we did for repetition code, but now for correcting both bit flip and phase flip errors. And because there's two types of errors, we have to go, like just a line is not enough, we have to go to a square, where you can think like one dimension correcting bit flip errors and the other one correcting phase flip errors. So there'll be a lattice of qubits defining a quantum code. This is a quantum code that has only one logical qubit encoded. The white dots, they are the data qubits. So there will be like d square data qubits, right? Where d here is distance 5 in this picture. And then we also introduce ancilla qubits, which are qubits where we keep measuring them to try to learn if the data qubits were corrupted or not. So the ancilla qubits will be the black dots here. And instead of, let me go back here, right? Another thing that we could do, say, okay, suppose we treat this quantum mechanically, right? What is the operator associated to this operation of this parity, right? Of checking basically the parity of two nearby bits. This is just like a ZZ Pauli, right? Operator. So now here, we are going to do similar to before, but now instead of just checking the parity of two nearby bits, we measure the parity of 4 nearby qubits. So we have a stabilizer, right, that was introduced in the other lecture, a ZZZZ stabilizer that we measure here, these red ones. And we also, now we want to do the same thing, but for phase flip errors. The nice thing is that bit flip errors are connected to phase flip errors by the Hadamard gates, right? So we can just Hadamard all these ZZs, we get XXXX, and this will correct the phase flip errors, again, looking at 4 nearby qubits. How we do it, right, in practice? Well, in practice, we have a circuit to do it. So let me introduce the circuit. So the circuit to measure the ZZZ Pauli, ZZZZ Pauli matrix is that introduce ancilla qubit, right? This ancilla, the black one here. And then, you prepare the ancilla in the ground state, in the 0 state. Then you do a bunch of control CNOTs between each of the data qubits as the target and the ancilla qubits. So you do 4 of them. Then you measure in the plus-minus basis, or you apply Hadamard and measure in the computational basis. And my claim that this basically measures this observer ZZZZ. If it's not clear to you, just try to check it out. I think it's a very good exercise. You can do the same thing for the XXXX. Again, they are changed by a Hadamard basis, right? So if you Hadamard everything, you end up in these similar circuits, but now the CNOTs, they're in the reverse direction, but it's a very similar circuit. So this is how physically you do it, right? So you think that you have these ancilla qubits, they are here. Each one of them, you apply CNOT gates to each one of the 4 data qubits, and then you measure the ancilla qubit, you get a bit of information, and then you keep doing that. That will be how you do the quantum codes. That's how you operate all the time, applying CNOT gates to try to interact with the data qubits, measure the ancilla qubit to extract 1 bit of information, and keep doing. You have to be done in a way that you don't corrupt the information, right? So you only want to learn about kind of this parity, right? About the, if you're in the plus or minus 1 eigenstate of this stabilizers, and you don't want to learn anything else. Okay. So I think this was mentioned before, but I'll go a little bit quicker here. So first, you can check a few things, right? Why this works. So first, you can check all stabilizers they compute, right? So why? Because the stabilizers, they will overlap always in pairs, right? So these 2 stabilizers, right, they overlap in these 2 qubits. This and this stabilizer overlap in these 2 qubits, but then a XX touches ZZ, Pauli matrix anti-commute, so XX commutes with ZZ, so they all commute. And it can also check just by, if you multiply all of them you get identity, and then you check how many independent, how many of them you have, and then you can find, there's boundary ones which are different, right? They are 3-body instead of 4-body, but then it turns out that there is a common eigenspace of eigenvalue 1 of all these Pauli matrices, and it's 2-dimensional, and that's exactly the logical qubits that you want. What are the logical X and Z operators, right? So they are just strings that go throughout the lattice here. So here, this will be an example of a logical X. This is an example of a logical Z. It's what we call a topological code. So you can deform things, and if you deform by a topologically trivial way, nothing happens. So your string could also come here for X, go around here, go back, and so on. This won't change. But as long as it's a topologically non-trivial string, like here, right, that connects two boundaries, this is a logical X, and this is a logical Z. Okay, so how correction will work here? Well, it will be very similar to what I told you about this kind of repetition code, but now you use this stabilizer checks. So suppose you have so first X error and Z error. Let's assume like a stochastic error model, right? They happen each one with some probability independent from the other. So you correct X error completely independent of Z errors. Okay, so for correct X errors, you only have to think about the Z stabilizers, and for correcting Z errors, only about the X stabilizers. So we can do that independently. So now suppose you have an X error as here, and suppose you measure all the stabilizers, right? So there will be a scheduling for measuring stabilizers in the optimal way, but just think about now, forget about this, you're just measuring all of them. You can measure them perfectly. That's another abstraction, but let's do this for now. And then, they will all deliver +1 outcome, but these two, they will flag, and they'll get like -1 outcome. And because these two flag, then you say, oh, okay, I got an error X here. Okay, very similar to the rep codes. Now you have a Z, the same thing, but now the two X stabilizers will flag. These two will flag. Then you know that you had a Z error here. Now suppose you have two errors, right? XX here. Then again, you measure all the stabilizers, and now those two will flag, right? This one and this one, the Z stabilizers. And then because these two flags said, oh, okay, I'll have, the error was these two X's here, and so on. So, the general idea is that if there's a string of errors, right, either X or Z, we can treat X and Z separately again. If there is a string of errors, like Z, for example, the two stabilizers at the boundary of this string will flag. Okay, both will give -1. And then, if that's the only error you had, you could infer that there was a string of errors. Yes. Oh yeah, great point, right? So the question is, okay, now suppose, which I think I'll get later, but let me mention already. Suppose these two flagged, right? These two. Then my claim is, okay, these two. The only way for these two to flag is there is a string connecting them, right? But is the string unique? It's not, right? So the string could also, you come here, right, and then maybe you go here and here, right, and then you come back up to here and here, right? So so this is like a degenerate code, right? So you give the same syndrome information for a whole class, right, of different error configurations, but it's fine, right, because the two errors, they are equivalent up to kind of a closed loop inside, and this does nothing to the information. So you don't care about that. That's right. That's right. Yeah, there'll be the dangerous case, but I'll get to that. All right. So and I think this was already covered, right, in Yoshi's lecture. So just to remind you, and this is not the bosonic part yet, right? So this is just like just idea of quantum error correction. But now when you're in trouble, right? Going back to the question. So suppose these two flagged, and you say, oh great, I think I have this string connecting them, Z. Let me correct for it. Let me apply Z here in the lattice now, right? In the memory now. Okay, great. But what if actually the string was this one, which goes around, right? So a ZZ here and then a ZZ here. That's another string, which would also give these two as flags, as violated stabilizers. And actually, if you, instead of having this one, if you actually had this one, but you think you had the other one, and you try to apply a correction, right? Now you apply Z here. and now you have a closed string of z's, right? And I told you that a closed string of z's, topologically non-trivial, that's a logical z. So now you have corrupted your logical qubits, right? So now you have introduced a logical error. So this means that a wrong correction can lead to application of a logical z, right, or logical x in the case of x errors. And what is the chance? What tells you when you are in this danger case? Well, this is when the error, right, is of weights, right? The weight is like the number of non-trivial stabilizers or non-trivial Pauli matrices when the weight is bigger than d over 2 minus 1, where d is the distance of the code, right? So a surface code of distance d can correct up to d over 2 minus 1 errors, right? Because when you are about half d over 2, then you can have this situation, right, where you think you had 1, but you had the completion, right, of a topological non-trivial loop of this one, and then you're in trouble. So this gives like a sense of how much, right, errors you can correct, similar to the rep code you can correct, right, like also some people, right, that goes with the distance of the codes. Now, this I won't tell the details, but that's not the whole story, right? Because now what will happen? What will happen is that you have a distribution of z errors, right, a distribution of x errors, and you have to correct them. And then you say, oh, okay, I have only the syndrome information. Like, this stabilizer was -1, this one was -1, this one was -1. How can I try to guess what is the string of errors, right, that lead to this distribution of outcomes that I'm seeing? So there is an algorithm that can do that. There's many ways to decode, right? This is about decoding, right? How you go from the syndrome information, from the values of the stabilizers that you measure, to the correction that you have to do, to inferring the error that happened into the correction you have to do. There's many algorithms. One popular is minimum wave perfect matching, right? So the idea is just you want to do some kind of matching, right? So you just have like these pairs of violated stabilizers. You can even think about this is like a topological, right, code, is some kind of like anions if you want, and then you want to match them by applying strings. Of course, higher weight strings, they are less likely to appear, right, because we're assuming this independent error model. So longer strings, they are less likely, so we disfavor them more. So there's like a weight that we give, which is just the number of non-trivial Pauli matrices in the string, and we want to do a matching. We want to pair up all excitations that we saw, but we want to pair in a way that the length of this, right, of the matching of these pairs, which is just the length of the Pauli string connected them, is the minimum possible. So this is called this minimum wave perfect matching algorithm for surface code, which was discussed in the other lecture. No, it's more complicated than that actually, because the stabilizers, right, how you measure the stabilizers, I showed you before, right, which is by this quantum circuit, right? Let me show you again. Where is it? Okay, this, right? So what I assume, what is the setting that I've been assuming? That you have a distribution of errors, it happened, and then you can perfectly measure the stabilizers, right? And then get some syndrome information. That's not what happens in practice, right? So actually, you have errors happening, but of course, to measure the stabilizers, you have to implement these circuits, right, on all these qubits here. There's a scheduling to do them in parallel. But while you're applying the circuit, errors keep happening, right? So in between these C-naughts, there's like errors happening. And because the C-naught is a 2-qubit error rate, this error, even they might propagate, which was a single error here, for example, might become a correlated error. So there's like a propagation of error, which is luckily not so bad because it's a very short depth, right, circuit here, but you have to handle that. And then to do it, let me go back to here. To do it, what happens, this is a picture from a paper from Google where they do this kind of error correction experiments. You have to do a similar kind of perfect matching with the minimal weights, but also thinking about errors that happen in time, right? Errors that happen while you're trying to measure the stabilizers. So it's a more complicated matching problem. It's a 3-dimensional matching problem instead of a 2-dimensional one. You end up in this kind of plots, right, where you have space-like errors, which are errors in the qubit, but also like time-like errors, which is errors that happen when you're applying the gates to try to measure the stabilizers. Right? Again, it's a matching problem you can solve, and if you do it, you end up with this kind of physical picture, right? So everything that I told you, you can abstract away, and then the main message about the surface code is that it's a logical qubit. because of this kind of matching algorithms, you can come up with an expression for the logical error rate, is this epsilon L here. And the logical error rate will decrease exponentially with the distance of the codes, actually with d plus 1 over 2, right? Exactly because of this thing, right, that can correct up to d plus 1 over 2 errors. With a base of the exponent, which goes as, okay, in the abstract error model where everything, all the components, they fail with probability p, there'll be the physical error rate p, but not directly the physical error rate, but normalized by a constant. And this constant, p threshold, is a property of the code and of the decoding algorithm, right? So given the surface code and the minimally perfect matching, we have to numerically estimate p threshold. If I give you a different decoding algorithm like union find, I have again to estimate this p threshold, right? So it's a constant, but it's a property of the code and of the decoder. And that's the expression for the logical error rates. And then there's a prefactor, like numerically for surface code is like 0.1. Again, it depends on the error model. Of course, the threshold also depends on the error model, right? So three things: depends on the codes, on the decoding algorithm, on the error model. What is the error model? Is the error rate of all the components, right? So it's like, what is the error rate of your 2-qubit error rate, right? What is the error rate of the readout? What is the idling error rate? And of course, the error model as well, right? You only have the polarizing error model. Maybe you have some dephasing, right? Maybe you have amplitude decay, right? Amplitude damping, and so on. So this is all like inbuilt here. So this is how theorists like to talk about, right? Like the performance of the logical memory. Just a number, physical error rate divided by threshold is very elegant. And we can talk about threshold, and I'll tell you what this is for the surface code. But because this is an abstraction, right? In reality, you have all these different error rates and all these different, for the components. Experimentally, we like to talk about the lambda parameter. So the lambda parameter is how the logical error rate drops when the distance grows. So in this abstract model, lambda would just be p threshold over p, right? So the smaller the physical error rates, the bigger lambda. The bigger the threshold, the bigger lambda. And then the logical error rate is like 1 over lambda to this power of d plus 1 over 2. Okay, so all right, so this is what I was telling you, right? P is the physical error rate. D is the code distance. In this case, the d by d for the surface code. The threshold for the surface code is around 1%. So it's a nice thing about surface code. Threshold is not too low. Again, it depends on the error model, but that's kind of a good rule of thumb. And of course, this epsilon L is the logical error rate that I mentioned. How we are doing this, how far we are in doing this experimentally, right? So now what's the goal? The goal is to increase lambda as much as possible, which means making the components as good as possible, p as small as possible. First, error correction doesn't always work, right? So suppose the physical error rates, p, they are just bigger than the threshold, right? Suppose p is bigger than p threshold. Then what this expression shows, it shows that error correction is a error enhancing protocol, right? The error just goes up, right? If you encode. So that won't be good. You shouldn't do error correction. Only when the components are smaller than the threshold, and hopefully substantially smaller than the threshold, right? Because otherwise the drop off is very slow, is that error correction pays off. And that's the reason why, only kind of recently we start having these error correction experiments, right? Because before we just not below, the experiments were just not below the threshold for error correction. But now they're starting to cross, which is exciting. And the other thing is that once you're below the threshold, then the error drops exponentially with the distance, right? And now, basically this is what we want to see, right? And we want to then get lambda sufficiently big, maybe 10, maybe bigger, ideally. And then we want to get this distance big enough that we end up in this, error rates that we need for applications like 10 to minus 10, 10 to minus 11, right? And so on. What is the state of the art? 2 experiments the paper was 2025, but maybe the archive was 2024. Google using superconducting qubits, using the surface code that I present to you now, of distance 3, 5, and 7, right? They end up to distance 7. For distance 7, how many qubits they use? Well, it's 7 by 7, right? So 49 for the data qubits, but you have to double for the ancilla qubits roughly. So it's something like 96 or so qubits, roughly. They ran this experiment. They computed lambda experimentally, right, empirically, and they saw a lambda of approximately 2. So the logical error rate per round was decreased by a factor of 2 from 3 to 5 distance, and by another factor of 2 from distance 5 to 7. It's pretty cool, right? It's like definitely below the threshold. And they could repeat this experiment many, many times, where they keep measuring the stabilizers and they keep, checking the performance. So they did like thousands of repetitions. Also with atoms, recently, last year, they also got a roughly lambda of 2. In this case, from distance 3 to 5. One caveat is that one challenge of atoms right now, they just fly away, these atoms, right? So there's like a atom loss that you have to handle, which again, going to the question, is a separate type of error. It's not just X and Z, right? But you have to handle. And because there was a lot of atom loss there, they could only do like 4 rounds of error correction, and then it wouldn't work anymore. Of course, there's ways to try to protect for that and improve, but that's kind of the state of the art, right? So, yes. That's the billion-dollar question, right? That everyone is trying. Many people are trying both, and the weight you put each one of them, it varies, right? So I would say, for example, Google, and they have been very successful. They are trying the first thing you said, right? They say, okay, I have the transmons, I have this error rate kind of 10 to minus 3. My lambda is 2. 2 is too bad. 2 you should not scale yet. But they say, oh, maybe I can improve 2 to like 7 or 10, and then I'll just scale, right? And this is my pixel, and I'll just scale. Fair enough. That's a strategy. But then the scaling will be a lot, right? So you have to scale. I'll show you like 2 millions of qubits. That can be daunting, right? The other maybe extreme example was like this, Majoranan fermions, right? Microsoft was saying, oh, let's just find the perfect qubit, right? Well, we don't even need the error correction. Maybe lambda will be like, like 10,000, right? And then I'll be good. But then, right, you have to find this very good qubit, which can be challenged, right? So, and there's all kinds of proposals along the way. There's also things you can do, like where you go beyond surface code, which I also mentioned, which is a good game to play. So there's definitely this thing of lambda versus scaling. That's one. And there's also don't do surface code, do some other kind of codes, which maybe are more challenging to implement than surface codes, but that also gives you like less overhead. So this will be why I'm going to bosonic error correction, by the way. So I'll give you our own flavor of that. But no one knows what is the right thing to do. But I think that's fair to say. Okay, yes. It's another good question, right? If lambda is really a constant or not. I think it depends on the platform. So, for example, for superconducting qubits, and we don't know for sure because we haven't scaled yet, right? So, but for superconducting qubits, suppose you want to do like, well, let's call it the Google approach, right, of scaling surface code. Then I think up to some scale, which we estimate maybe will be like 1,000 qubits, which is the scale you can fit on a single silicon chip. Then I think lambda will roughly be a constant because everything's just these local connections there, so it shouldn't matter too much. But there will be this scale where it doesn't fit in the chip anymore. And then you have to have multiple chips and connect these multiple chips along the boundary, maybe with some, probably with some microwave lines. But these connections, there will be lower quality there. So then it will be a different kind of error rates at the boundaries, right, of this 1,000 qubit block. And therefore, indeed, lambda will change in that case, right? And there's similar considerations for all. So you're right, it won't be the same lambda all the way to like millions of qubits. But I do think that in most platforms, it's roughly constant up to at least 1,000, maybe a little bit more. Yeah. It's a good question. Let me show you why in this example. So look at that. So let's do lambda 10, right? And now this is what requires with surface code. Okay, this is the logical error rate that you need to factor a number to break RSA 2048 with Shor. So you need 10 to the minus 14. And that's just because you have, like thousands of qubits. So this gives a 10 to the 3 factor. You have tens of billions of gates. It's like a 10 to the 10 factor, right? So the product is like 10 to the 13. You want to do a little bit below, right? So 10 to the minus 14. So if you look at this expression that I just showed you, you can compute and you find that you need distance 25. How many qubits you need for one memory, for one logical qubit? Well, it's what I told you, right? So you have 25 by 25, 25 square. data, 25 square on Silas. So 2 times 25 square, this is 1,250 physical qubits per logical qubits, right? Which is a lot. Now think about 2, right? If you think about 2, then, right, is roughly a factor of, because it goes as the square, right? The number of qubits goes as the square of the distance, right? So lambda, it would be a factor of like, a factor of 10 more, right, roughly, right? So in that case, for lambda 2, you require like 12,000 qubits, right? 12,000 physical qubits per logical qubit, right? That's a lot, right? Even lambda, it seems a lot, right? So and this goes to the question, right? So okay, the scaling is great. Getting lambda 10 first is very challenging for everyone today, right? No one could do it, so that's the first challenge. The second challenge, even if we get to lambda 10, is a pretty daunting scaling task, right? So you have to scale overhead of thousands, right? And I'm only talking about memory, right? If you actually do computation, which maybe was also discussed by Josias, but it was kind of, you have to do lattice surgery, right? Which has a little bit of overhead. You have to do magic state distillation or cultivation, which has a little bit of overhead. This gets worse, although these days actually the memory actually dominates the footprint, so it's not a bad approximation, but it's a lot, right? So if you want to operate on thousands of logical qubits, as you want to do, if you want to factor a number, or if you want to compute a complicated molecule, the ground state energy, then you need millions of physical qubits, right? So that's the conclusion. All right, so let's try to get to millions of physical qubits, right? I think it's a great goal. But also there is this other question, right? So can we find a more efficient approach, right? And again, that I mentioned before, that for a long time, surface code was the only game in town, right? Everyone said, okay, that's surprisingly was one of the early codes, right? It was introduced by Alexei Kitaev in the 90s, early 90s. And then for a long time, said, okay, it was the first code that, there's a actual anecdote about that, which I don't know if it's true, but I think it is, which the surface code was the best code, the only code that people thought could scale for like, 15 years, 20 years. And then they asked Kitaev, how you came up with this code, right? So, which is so good. And the first one that you proposed, he said, I thought about all the options and that was the best. So, but he was wrong actually, right? Well, maybe he was wrong, because actually in the past 10 years, suddenly people start exploring many different options for error correction. And many of them are promising, and maybe they can disrupt the surface code. Many of them actually are inspiring the surface code and do tweaks to the surface code. So maybe the surface code still stands. But there's more to say, right, than just let's scale surface code. I think this is definitely true these days. Okay, so one game you can play is keep the surface code, just improve the accuracy of the experiment and increase lambda, right? And that's definitely something that we have to play right now, because lambda is just 2. And this is like the state-of-the-art experiments, right? And 2 is not good enough. We want at least lambda 10, I think. But actually, if you keep increasing lambda, there is diminishing returns. So that's one observation, right? And let me write an equation. So no, remember that you have like lambda to the minus d plus 1 over 2, right? That's the logical error rate. Some constant, doesn't matter. And now, what are the number of qubits, right? How many qubits you need for the logical block? Well, this is roughly 2 times d squared, right? So now, suppose you have lambda. Suppose you had lambda 10, and you go from 10 to lambda 100, right? Which means like improving your physical error rates by a factor of 10x, right? You have like 10 to minus, right? Roughly, because the threshold is roughly 1%, lambda 10 for surface code means that your physical components, the error rate is like 10 to minus 3, right? So every 1,000 operations, there is an error. That's pretty good, right? Suppose you could improve that every like 10,000 operations of gates or readouts, you have 1 error, which is pretty challenging experimentally, but maybe one day. What will be the improvement in the overheads, right? Well, so now here, instead of 10, you have hundreds, right? So because you have hundreds, the exponent, right, d, and this we can forget about this, right? Is proportional to this. So because lambda instead of 10 is hundreds, the distance can be twice as small, right? But now if the distance is twice as small, and the number of qubits, which is kind of the overhead, goes as distance squared, it means that going from lambda 10 to 100, the overhead goes from, becomes 4x smaller. So it's if you can do it, great, right? But you see, okay, it's like 10x improvement physically for a 4x improvement in overhead, so it's already smaller than maybe you might expect. Now suppose you go from 10 lambda, right? So which I also wrote like, now suppose lambda instead of being 10 is like 1,000, right? So now you have improved the error rate like 100x more, right? So now your physical error rate is like 10 to the minus 5, right, for the gates, extremely small. Then you can play the same game again, right? So it's 10 to the 3, right, instead of 10. So then the distance can be 3 times smaller, and the number of qubits goes as square of the distance. So then, the overhead is only 9x smaller, right? Which, great, I'll take this, right? It's the order of magnitudes, but you had to improve 100x here, right? So it's diminishing returns, right? So the error correction, if you're above the threshold, is the death zone, right? Don't do error correction. If you're just above the threshold, you can do it, but it's extremely inefficient, right? And if you're substantially below the threshold, you start getting some kind of logarithmic improvements, right? So there's diminishing returns. So if you have such a very high control for your experiments, right, that you can achieve these very impressive lambdas, you might want to do something else than just doing surface code, right? So this is this point, right? You can improve lambda, but there is diminishing returns at some point. But maybe you can get some. You definitely will get some savings. And right now, this even is kind of very much in the future, right? Because you don't have lambda equals 10. Lambda is like 2 or even worse. Now, what are other ideas that maybe can give this kind of order of magnitude improvements without such a huge cost, right? They will have a cost, but maybe the cost is not so huge. So there is like probably more than 3 ideas, but let me mention 3 ideas. So there will be the idea that I'll be discussing in the maybe second part of the talk. I'll start now and continue then, which is, suppose there is a way in the lab where you can engineer your qubits that one type of error, bit flip errors, are much smaller than phase flip errors, right? So you're clever about your qubits, right? So let's think about the transistor again, right? The transistor is a bit flip. There's only bit flip errors, and px is 10 to the minus 19, right? So say, okay, forget about it, right? Now suppose that you have a quantum bit, a qubit, but suppose it's kind of half a transistor, right? Suppose px is like 10 to the minus 19. Say, okay, there is no bit flip error. I don't care about it. You still have to correct the errors, right? But now it's much easier. It's just one type of error, right? So that's one extreme case of bias noise. In reality, we don't have credible ways of making px 10 to the minus 19, but we can make it much smaller than pz. And then you need less overhead. Many ways, again, you can use this. But one simple way is that, as I mentioned before, the surface code, right? This d by this surface code is because one direction is to correct bit flip errors, the other is to correct phase flip errors, right? Which you can note by the way you're thinking about, right? These stabilizers and these strings. Now, if bit flip errors is much smaller than phase flip errors, you can squash one dimension. You can squash the dimension that was correct for phase flip errors, and then you can gain overhead, right? Instead of a d by d surface code, maybe you only need a d by 3, for example, surface code, and only correct one, right? You can correct one phase flip error. So you kind of square your physical px, and maybe that's good enough, right? So that's one strategy, and there is other ways to use this too. There is what was mentioned, right, in Yossia's lecture towards the end, which is this idea of using quantum LDPC codes, which I won't cover, but it's very promising, and especially, right, was mentioned before. I think we will see a lot of progress. Yesterday there was a paper by Continuum doing this with ions, very exciting paper. I think we start seeing the next few years papers on Rydberg atoms as well, implement these LDPC codes, which will be exciting. And the idea here is that surface code, right, I show you need 2D square physical qubits to encode one logical qubit, right? But what if actually there is other choices of codes for which you use, for example, n is the number of physical qubits. What if you use n physical qubits, right? So let me write this. For surface code, right, you encode one logical qubit. using n physical qubits. For LDPC code, the idea is that maybe you can encode a constant, which we have to see what this constant is, times n logical qubits. So there's like a constant encoding rate, right? You don't encode one, encode multiple logical qubits. And asymptotically can even be a constant rate. Of course, you usually care about finite size codes for error correction, but you can encode many. And for a long time, of course, classically you do that a lot actually, right? Whenever you send again communication for optical fiber, you use LDPC code. There is extremely good classical LDPC codes. So good that this constant is actually kind of like very close to 1. It's like 1.2, something like this. Sorry, it's like 0.8, something like this. Can be extremely good. Of course, they don't, it only protects memory, right? So you don't have to think about errors in the computation. So it's easier. But for a long time, we had no idea how to do LDPC with quantum. It was very challenging. But then, as was mentioned in the other lecture, right, there was like many breakthroughs in the past 7 years or so, where we do have many constructions, some of them even potentially practical. So this is an example of a plot from a paper by IBM, where they introduced this like gross codes, this bivariable bicycle codes, BB codes, which, for example, with 144 qubits, right? So you can encode 244 physical qubits. You can encode, for example, 12 logical qubits, right? So much better encoding rates, right? So this gives encoding rates of, including ancillas, right, of 24, right? Which is much better than these numbers that I showed before, right? The logical error rates, maybe to get to this algorithm relevant, you might need encoding rates of like 50, something like this, but it's much better than 1,000, right? So there's definitely potential for like an order of magnitude improvement, right, over surface code estimates. But the price you pay is that you have to do long range gates, right? So this is one code that they introduced, which is very nice because it's a tweak of the surface code. You have the surface code interactions as before. You have these local stabilizers, the XXX and ZZZ. Well, not quite. So you have like XXX, XXX, but now it's a 6-body stabilizer, and 2 of the Pauli matrices, they are long range. So one of them, it'll be the one here, right, which will be like 7 by 7 away, and the other one will be maybe, well, I think it's more like 3 by 7 and 7 by 3 away. So it's like the 6-body check all X, similar to the surface code. 4 of them are local as the surface code, but the 2 extra ones, they are long range. And this is in the torus. You can do also, you can also do closed boundary conditions, open boundary conditions, but then the encoding rate is a little bit worse by a factor of 2. But the game to play here is find a way to implement long range gates, which is more challenging usually. But then there is a payoff, which is the overhead will be smaller, right? And for the codes that we know, these overheads, I think it's fair to say that in practice it could be like a order of magnitude smaller, maybe even more if you can find very good codes. Usually these very good codes with encoding rates much better than these BB codes require very, very long range, right? Like long range across the whole, like 1,000 qubits, right? Or 5,000 qubits. That become more challenging. But there's this trade-off you can play. So ions will try that. As I mentioned, is already doing that, which is exciting. Atoms will be doing that very soon, I believe. And superconducting qubits, you could try to do it, but now you have to develop this wiring, right? This long-range wiring between qubits, right? So everything has to be in a plane, right? As I showed you before, with we can actually build multiple planes, but not like maybe 10 planes. 3 planes is common for the wiring, maybe more. You have to make this connection between planes very, very good, high quality, which is hard. And then you have to distribute this wiring, right? So you have to distribute a wiring between this qubit and this qubits across a few number of layers. That's pretty challenging, but in principle it's possible. For like a flash memory, classically people do more than 30 layers, right, of different chips. So this chipping stacking is possible, but it's challenging. And IBM, for example, that's how they are planning to do things, right? So they're trying experimentally to implement this. They couldn't yet, but I think it's hopefully it's possible because it would be very exciting for superconducting qubits as well. Yes. Yeah. Right. Yeah. The question, right, which is a good question, is okay. So suppose you only have 2-dimensional connectivity, right? Can you still apply this idea? Just swap the qubits, right? Do swap gates, to mimic the long-range gates. So you could try to do it. There's a paper that analyzes this, but then doesn't really, the payoff is not there. It's not worth doing. That was the conclusion. One thing that you can do, and probably actually we know is actually already helpful, is that so surface code, even for two-dimensional connectivity, is not the final solution. You do surface code for patches, you get the logical qubits, but now on top of the logical qubits, you apply a concatenation of a code with a high encoding rates. You can do LDPC, but one that works very well is not LDPC because LDPC is local density parity check, right? So each stabilizer is kind of constant. This high encoding rates called yolk codes from Craig Gidney and collaborators is a very high weight stabilizer, but you don't care because it's at the logical level, right? So you can pay this high weight price, but then you can get an extra square in the error rates at no additional overhead costs. So these estimates for the surface code, right, they get reduced by between 3 and 4 factor. So definitely at the concatenated level, you can do something more sophisticated, but at the physical level, the swap network so far, with they don't give the value. Yeah, the solution that we should always do now, it's yeah. Actually, in that case, you don't do the swap. You just actually concatenate in another code, but it's a code with extremely high encoding rates. So the C of the code there, this C is 1, and very very close to 1. It's like 1 minus 1 over n, and but the weight of the stabilizer is also n body, but you don't care at that point because the logical error rate is so small that you can pay the price. Yeah. Okay, and there's another idea which is done. It has been proposed for superconducting qubits. We also work a little bit at Amazon on this, but also people are proposing Rydberg atoms, like Jeff Thompson group, for example, which is exciting. Is the idea saying the following: suppose you have some type of error, right? And a common type of error is, for example, some kind of decay, right, of the atom, or decay of the excited state, right? So some energy loss in the system. And suppose this energy loss, you could kind of flag it, right? So kind of you could make a measurement and determine that there was this energy loss there. Then is an error, but it's a flagged error, and this is called like erasure error. And because actually in this case you know that the error happened, is flagged, then error correction is much more efficient, right? And the threshold can be much higher, and therefore the overhead is much smaller. So here is similar game. You try to engineer your qubits, but in a way that the dominant source of error, which you call E, erasure error, is much bigger than the residual error, the error that you cannot detect, called like Pauli error, P, and then you can have a gain. So for example, maybe E is 10 to minus 3, but P is like 10 to minus 4, right? And then it's basically saying your effective lambda is not like 10, but it's close to 100 maybe. So that's one example how you can do it. Superconducting qubits very simply. There's also atomic examples. So suppose you, instead of 1 qubit, you use 2 qubits. Instead of encoding 0, 1, you encode 1 qubit, the logical 0 in 0, 1 minus 1, 0 in the singlet state, and the 1 in 0, 1 plus 1, 0, right? So encoding the phase of this, of 2 qubits with 1 excitation in them. Now if there is 1 photon loss, right? If there is 1 energy loss event here, 1 photon gets lost, both of these guys will go to the ground state, right? To 0, 0, because there was only 1 excitation. So suppose that every gate, or every few gates, you just measure if the qubit is in the 0, 0 state, and you do not discriminate if it's, in any one of those, which you can do. Then you detect that there was a erasure error, and this is the dominant source of error, because energy loss usually is the dominant, right, like source of error, and then you can have more efficient error correction. So that's another idea that people are exploring as well. Someone had a question? Okay. All right. So I should end up very soon, right? All right. So these are the ideas, right? And the one that I want to focus, and this will be my last slide before lunch, is on, is on this one, on bias noise, right? How we can engineer a way to get bit flip errors way smaller than phase flip errors. And the approach that I'm going to do for that is what we call bosonic quantum error correction. So let me just tell you, very generalize this slide, and then we stop. The idea here is that how is the standard approach that we've been seeing so far, right? The standard approach is that we have two-level systems, which, as someone point out rightly, they're not really two-level systems, right? They have more levels, but to a good approximation, the two lowest levels are the most important, right? And then we use many qubits like this to form a code, like surface code, for example. And that's how we define our logical qubits. But now, right, in practice, in an atom or in the superconducting qubits, you have actually many energy levels, right? And you can even have, for example, what we use, you can have a box, right? It can be like a strip line cavity, or it can even be like a phononic band gap cavity for phonons. You create a box that has a harmonic oscillator there. So you have like infinitely, in principle, like equally spaced energy levels. Of course, there's an energy cutoff, but they have many energy levels that to you, they're equally spaced. And now the idea is, well, actually this, right, this is the energy level of this boson there. That's why bosonic error correction. Can we use all these extra levels instead of just the two lowest one to do this encoding, right? So instead of using many two-level systems, let's use one very high n-level system, very high n-level system, and maybe try to find a clever encoding of information in these energy levels that protects, right, and does the error correction in a more hardware efficient way. So the idea here is that you have one physical oscillator, many energy levels, and then you use not necessarily two of these levels, but you use two states in this Hilbert space given by this kind of harmonic oscillator to define your bosonic qubit, which should be protected, right? Should be doing some kind of error correction. So you want to do some hardware efficiency through the infinite dimensional bosonic qubit space that we have very naturally in the lab, right? There's a lot of great work that has been done in the past years on that. I'll tell you after lunch, and then I'll tell you how we are using this approach to try to get this bias noise and try to get an improvement in error correction. So let's stop here. Thank you. Question before lunch?